Okay, so we just get done going over the electronic structure and electronic function of the electronic structure of an atom, and then determining how an atom can function to have its functionality due to its structure. All right, so now what we're going to do is look at molecules. And remember, molecules are two or more atoms chemically combined into in a specific arrangement. Okay, and what we're going to look at now is that thing called chemically combined. And we're going to briefly talk about ionic bonds. So the chemically combined is, in chemistry, we call that a bond. And for ion, so first thing we'll do is talk a little bit about ionic bonds, and then most of this will be the rest of this and the rest of the next video as well. We'll concern ourselves with covalent molecules, which the bond is called a covalent bond. All right. So again, what we'll do is we'll study structure, okay, and then we'll end up. And that's what this video will be about. And then the next video will be related to function. Right, ionic compounds. So ionic compounds, I think, are pretty easy to understand. We have similar types of things in our lives that kind of relate to it, like magnets. You know, have your North Pole and your South Pole. So ionic compounds are going to be kind of alike, like that. But instead of having magnetic interactions, they have electrostatic interactions. So and we'll talk more about electrostatic interactions when we talk about in the next PowerPoint as well. So electrostatic are like magnetic, but dealing with electricity, and you've probably experienced electrostatic. It's like, I don't know if you ever had a balloon and you rub it on your hair, or the balloon will stick to your hair, or you know, if you go to the dryer and try to pull your socks out, they might be stuck together. That's because of the charges on the different parts are opposite, and then they attract each other. So in terms of ionic compound, you have two oppositely charged, electrically charged substances, and we'll look at like sodium chloride. Okay, where sodium has lost an electron somehow and then becomes has a net positive charge, and chlorine somehow has gained electrons. They could be, how they gain or lose electrons can be independent of each other. And then if you bring these guys close enough together, what will happen is they'll stick together. And that stick together is called is electrostatic interaction, right there. And we call specifically, since it's between ions, we call it an ionic bond. Okay, now one of the things that I just want to make sure you understand, especially when we get to the next video, is that bonds are interactions between atoms and molecules. Okay. So that's it for ionic compounds. All right, so let's get into covalent molecules. So how do the atoms stick together in covalent molecules? So in ionic, they stuck together because of the opposite charges. Well, it doesn't work for covalent because they're made out of nonmetals. Nonmetals, when they don't like to gain, they don't like to lose electrons, so you hardly ever have them with a positive charge. So you don't have this plus and minus interaction. Okay. So what makes them to get together? All right. So when I go over this, it's what I just said. It's a little bit more complicated than just having them attracted together like sodium chloride. All right, why do covalent molecules form? Why do they form ionic bonds? Okay, when you look at ionic compounds, the reason why they come together is because that reduces their stress, okay? Pluses like to be next to minuses, and when that happens, it reduces the potential energy and they become more stable. So the key is you always want to be able to reduce potential energy. So if covalent molecules, the same thing will happen once you reduce potential energy, but there's no attraction of charges. So what causes the reduction of potential energy? What happens, and it's fairly complicated, I mean, if you really look at it, but it's when there's a sharing of unpaired electrons. And we'll be using the Lewis dot structure to help us see this. Okay, for instance, so let's take a look at hydrogen. So this is the Lewis dot structure for hydrogen. Okay, and so what in this case, if this electron could go into a hole here where there's a unpaired, so this is an unpaired electron. Now this is paired up. Now it has a pair. And basically what it's doing is it's sharing another atom's unpaired, and then you get the same effect over here. So that's the only thing that's all we're going to say about it. What stabilizes the atoms in a covalent molecule is covalent bond, and a covalent bond is a sharing of unpaired valence electrons. Okay, how do covalent molecules form? Now we are going to try to figure out the structure of covalent molecules. We're going to find out their bonding structure, which is the connectivity between the atoms. Okay, so if you have water, how does the H's and the O's actually connect up with each other? And then what we're going to do, so this, we'll be able to demonstrate this as this right on the paper. It's two-dimensional. And then what we're going to do is try to, then what we're going to do is pull this out and try to look at it three-dimensionally as well. And then finally what we're going to do is see how this connectivity affects how the electrons are distributed on the molecules, okay? Because they're being shared, but are they being shared equally? And we'll get into that. All right, so let's look at determining the bonding structure, okay? And let's start out with water. The first thing you always have to do is you have to be given the chemical formula. You just can't come up with something random like C3F8 and think that it actually is has a chemical structure. Bonding structure. Okay, so so what we're going to do is you have to have the formula. Okay, next thing you need to do is draw the Lewis dot structure of all the atoms into a skeletal structure. And for water, basically what you do is just draw it like this. Okay, and that's the first step. You put the lone atom. Usually there'll be one atom there's just one of them. You'll put it in the middle, and the other ones you put on the outside. And usually you don't put things together like this. Okay, so you don't do like this. What you do is you try to kind of make it look symmetrical. Okay, once you have this, you add the dots, and that's what we have here. Okay, actually what you need to do after you get the skeletal structure, you need to count the number of valence electrons. Hydrogen has 1, oxygen has 6 valence electrons, and the other hydrogen has 1, so there is 8 valence electrons. So when we get all done with the structure, the number of dots on the total structure has to equal 8, and that's going to be a check. The other thing is when I do the dots, so I have my Lewis dot structures, I kind of line the, you don't have to do this, but I kind of line it up so that the holes in the pair are next to the holes of the other pair. Okay, so this is now the skeletal with the dots. So let's continue with this. Sorry about that. So now we're going to move the atoms so they move the electrons. That should be. So we're going to move the electrons, the valence electrons, so that one atom's dots fill the other atom's holes. Okay, so move that over here, and move that one over here, and now what you have is this right here. Okay, so you have this dot here now fills this hole, and you have this one right here filling this hole. All right, and then we do the same here and here, and we get this. Okay, and this is your bond. All right, so these are your covalent bonds. Okay, now at this step, what you do is you count how many dots you have. Now all the holes are filled up, so count the dots. So 1, 2, 3, 4, 5, 6, 7, 8. 8 dots. And remember, I said the dots now have to equal the number of valence electrons, and it is true. Okay, and let's go over that a little bit more. So, so that structure we just had. It's called the Lewis dot structure of water. Again, we count the dots. We see it's 8. So let's look at some here. Let's look at some things that happen after we form the structure. And let's look at each atom individually. So let's just look at this guy here. And you'll notice I drew it out here. And it has 2 electrons. Now if you look at the oxygen, okay, it has 8 electrons. 4 of them are shared, and then this hydrogen here has 2. You'll need to notice all the holes are filled. This means there's no more spots in the valence shell, so the valence shell is filled. And it turns out when it does this, it has the same number of valence electrons as noble gas, nearest noble gas. Okay. Nearest noble gas to oxygen is neon, and it has 8 valence electrons. The nearest noble gas to hydrogen is helium, and it has 2 valence electrons. So this is similar to what we saw when atoms become their most common charge. Okay. So in a sense, and it doesn't have to be, it's a pattern more than anything, is that after the atoms are bonded, their valence shell is filled, they achieve noble gas status. That means they have the same number of electrons as the nearest noble gas. Doesn't mean they turn into a noble gas. Okay, this is tricky if you think of it as that. They just have the same number of valence electrons. And they follow the octet rule. That means they have 8 electrons in the outer shell. Obviously, hydrogen doesn't do that. The reason it doesn't do that because it only has electrons in the first shell, which only can take 2. Okay, so these, for us in this class, these things will be true. All right. Okay, if you take higher levels of chemistry, we'll see that these rules may not apply. Exactly. All right. As for the Lewis dot structure, we often replace that shared pair. So we have okay. Here's what we got. Here's the shared pair and this shared pair. And what we do is we'll replace this with a dash. Okay. All right. And don't forget these guys. These guys are called the lone pairs, and they're very, very important. Don't leave them off. All right. So now what you have is you have this kind of looks like a stick, and it's actually kind of a good way to think about it. Is the oxygen stuck to the hydrogens? Okay. This is called a single bond, because there's only one bond between the atoms. Okay. Now, so one of the things you'll see is hydrogen will always have one bond. Just keep this in mind when we go forward. You'll never have hydrogen in between. You'll never have anything like this, okay? Where hydrogen is in between atoms because it can only have one bond. In this case, it looks like it has two bonds. So you'll see examples of that, but just keep that in mind as we go forward. All right, so in the end, I call this the bonding structure of water. All right, so let's do some examples of this, and then there'll be a worksheet related to this as well. So the first thing you do after you're given the chemical formula is figure out how many valence electrons you have. Excuse me. All right, so you can use a periodic table for this. Ammonia is in the 15th column. All the atoms in the 15th column, all right, will have 5 electrons. Okay, keep that in mind when you do this, is that you can use the periodic table to figure out how many valence electrons. And we're basically going to just deal with the last 6 columns, like from column 14 over. All right, column 14 will have 4 valence electrons. Column 15 will have 5 electrons. Column 16 will have 6 valence electrons. And column 17 will have 7 electrons. And then there's hydrogen with 1. Okay, so carbon and everything under it will have 4 valence electrons. Remember, you could remember the Lewis dot structure. Okay, nitrogen will have, and everything under it will have 5 valence electrons. Okay, remember there's 3 unpaired and 1 paired. Oxygen and everything under it will have 6 valence electrons, 2 paired up and 2 unpaired. And then fluorine and everything under it will have 3 pairs, lone pairs, and 1 unpaired. And then hydrogen, 1 pair. So these are your basic building blocks. Okay, so nitrogen has 5 valence electrons, and each hydrogen has 1. So there's 8 valence electrons. So this number here has to equal the number of dots when we're all done. Okay, so now draw the skeletal structure. Okay, usually what I do is I actually just draw it out without the dots first. Okay, and it doesn't matter how you do it. I mean, you could draw it like this, or you could draw it over here. Then add the dots to each one of the atoms. And then what you do is you fill holes. Okay. Now, so this is one bond, this is another bond, this is another bond. Okay, this is not a double. Okay, don't do this when you're done. All right, this means you're moving one electron into this hole and you're moving the other one into here. So what you have now is this right here. Okay, so when you get done, you have this, and this is your Lewis dot structure because all the holes are filled up. Okay, count the dots. Got 1, 2, 3, 4, 5, 6, 7, 8. 8 dots. And that equals 8 valence electrons, and voila, you're done. Okay. And what we're going to do is draw this in modified form in a second. But if you look, nitrogen has 8 electrons around it. Okay, so it has a full valence shell, noble gas, and etc. And hydrogen. Okay, and here's that I just told you about. And we replace these shared pairs with dashes. Okay, now you could have drawn this all kinds of different ways. You could draw it like that. You could draw it like let's put dots here, get rid of that, and H here. Okay, the main thing is you just show the connectivity between the atoms and the lone pairs. Alright, let's go to methane. Methane is CH4. Figure how many, count the number of valence electrons. Carbon has 4. Each hydrogen has 1. Equals 8. Now, so there has to be a total of 8 dots. Okay, now, the last 3 examples. Okay, the last 3 examples, they all had 8, but that won't always be the case. Right, so come with the skeletal structure, put the dots in, and then fill the holes. Okay, so you have one bond here, another one here, here, here. These are all shared pairs, so you have this. Okay. And then what you do is you replace, count the number of dots, 1, 2, 3, 4, 5, 6, 7, 8, which equals this, yay. And then you can replace the dots, shared dots, with dashes. And there you go. All right. Okay, now let's do some more. Okay, we're going to do these 4, and then there'll be a worksheet. Okay, carbon dioxide. First thing you do is you count the number of valence electrons. Carbon has 4. Each oxygen has 6, so it's going to be 4 plus 6 plus 6 equals 16. Okay, so notice this is not 8 this time. All right. All right. So so we need to have 8 dots when we're all done. I mean 16 dots. Right. Again, try to draw it symmetrical. You have C. Our carbon is your lone atom, so you put that in the middle, and you put the oxygens on the outside. Okay. You want it kind of symmetrical, and then put the dots in. Okay, and notice I try to put the holes kind of close to each other. All right. Now this one is going to be a little bit harder, but just fill it in. So you have one here and one here. So that's one bond. Okay, so that's a shared pair right there. Now these guys can share, so that's another bond. So there's actually 2 bonds between this. So there's 2 bonds. Okay, between this carbon and this oxygen. All right. Now we can do here and here. So that's another bond. And then we can go over here and over here. And we can see that this is a bond as well. So this carbon also forms a bond, 2 bonds with this oxygen over here. Okay. And there's also these 2 guys that were unaffected. So all of carbon's bonds are now unpaired electrons are paired up, and 2 of oxygens are being paired up. So what we're going to do is, instead of having this mess up here, let's move these guys. So that's one pair, and that's another pair right there. All right. So this is one, and this is the other one. This is one pair. So maybe that's this one right here, and then this is another one right here, which is this one right here. So it's a little prettier here. Okay. Okay, and you might notice is that I kind of have the dots sitting differently here than up here. It doesn't matter as long as they're there. Okay. Okay, so this tells me is that carbon has there's 2 bonds here. All right. So let's count the number of dots before we talk anymore. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which is what we said we want. Okay. All right, so and if you go through it all, you'll notice that carbon has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. So it completes the octet rule. Each oxygen also has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's Lewis. And again, just showed you what you did. Just make sure it follows the octet rule. And again, what we can do is we can replace the. Remember, these are shared, so remember these guys are the same as these guys right here. So it's not like these are all different. Okay, these guys here are the same as these guys here, but they're shared. So now we can replace each pair, remember, with a dash, and so we get this structure right here. Okay, in this case, these are called double bonds. They're like almost like 2 single bonds, but so they're double bond. All right, formaldehyde, CH2O. All right, so you're given the formula. Now figure the number of valence electrons. 4. Okay, then 2 times 1 plus 6, and add them up is 12. Come up with the skeletal structure. All right. So you have, in this case, you have 2 lone elements. You have carbon and oxygen. Okay. So which one goes in the middle? Well, a couple things. One, if you know the electronegativity, okay, remember electronegativity, periodic table, elements up and to the right have higher electronegativity, okay, or elements to the right have higher electronegativity, or going up have higher electronegativity. So if you look at carbon, oxygen, which one has a lower electronegativity, and that one should go in the middle. Okay, also, usually if carbon's all by itself, I mean, if there's a carbon, usually it's in the middle as well. Okay, so, right, so you're going to draw it symmetrical, okay, like that, all right, and then put the dots in, like I did right here. Okay, then fill the holes, okay, and I'll show you how to fill the holes here. So there's one bond, okay, there's another bond, and again, this oxygen can form another bond with carbon, and then you get this bond. All right, so what you're going to get here is you're going to get 2 bonds between carbon and oxygen, and 1 between each carbon and hydrogen. Okay, and so we get this right here. All right, so I kind of neaten it up. Here's your two separate filling of holes. Okay. Now you count the number of dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and that's what we expected from previous when we counted the number of valence electrons. So this is the Lewis dot structure of formaldehyde. Okay, and then what you can do now is we can replace the pairs with dashes, and that's what we do here. And this is the bonding structure. So formaldehyde has a double bond and 2 single bonds. And don't forget the lone pairs. We gotta leave them. That's important. Cyanic acid, HCN. So count the number of valence electrons. Hydrogen 1, carbon 4, nitrogen 5. So there has to be 10 valence electrons. Draw the Uh, skeletal structure, just told you in the previous one, carbon usually goes in the middle if there's two of them. Also, nitrogen has a higher electronegativity, so it's on the outside compared to carbon. Give the dots. Okay, so hydrogen, here's hydrogen. It has 1 unpaired, carbon has 4 unpaired, and nitrogen has 3 unpaired. And then start filling them up. Okay, so here's 1 bond. Now, between this carbon and nitrogen, there can actually be 3 connections. So 1, 2, and 3. All right, so there's 3 bonds here. Okay, so 1, 2, 3. Okay, and there's 1 over here, right here. 1 here, and then 3 here. Don't forget the lone pair right there. Okay, I'll count up number dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Check. Done. Okay, and then you can replace the shared pair with dashes like this, and now you got a triple bond and a single bond. All right, continue. Here's hydrofluoric acid. So how many valence electrons? 1 plus 7 equals 8. So we have to have 8 dots when we're all done. Skeletal structures is HF. Add the dots, or FH, doesn't matter how you do it, like this. Add the dots, and then fill the holes. And then you get this right here. Okay. Count the dots. 1, 2, 3, 4, 5, 6, 7, 8. And so it fits. And then you can replace the shared pair with the dash. Okay, so what I want to do here is just give you some overview of some patterns we might have seen that will help us in the future, and maybe a check. And if you take 121 general chem, you'll see me expand on this. But if you pay attention, look back at the examples that we just did, we'll see some patterns that came about. So the major elements we deal with as of yet are these 5 guys right here. Okay, and also this is in the 14th column, 15th, 16th, 17th, 18th. I mean number 1, 15, 16, 17, and number 1. Okay, really hydrogens is all by itself. But everything under carbon is going to have the same behavior as carbon. So silicon, okay, I believe selenium will behave just like carbon in terms of bonding. Nitrogen, everything under it, like phosphorus, will, and I can't remember who's underneath it, maybe arsenic, will also behave like nitrogen, okay? Oxygen and what's under it, like sulfur, is going to have the same kind of behavior. And anything under fluorine, chlorine, bromine, and iodine are going to all kind of act like fluorine when you bond. You'll see that these all have 3 bonds and 1 lone pair, 2 and 2, 3 bonds, 1 lone pair, and 4 bonds. Okay, and hydrogen always has 1. So let's take a look at this. So carbon, and everybody associated with this, so that'd be silicon and everything in the 14th column. Okay, right here. We'll have 4 holes, and wherever you have a hole, there's bond. Okay, and you'll always, and carbon will never have lone pairs on it. Okay, so you won't see any extra dots on it. And if you go back and look at the examples I have, like methane, it had 4 bonds. The formaldehyde had 4 bonds, okay, a double bond and 2 singles. The carbon dioxide had 2 double bonds, and then the cyanic acid had 4 bonds, but different. So carbon will always have 4 bonds, and they'll be in one of these 4 arrangements. So carbon will always have 4 possible arrangements, and it's be one of the 4. Then this will be a check. So when you're doing coming up with your structures, and you're filling the holes and things like that, go back and see if carbon has 4 dashes coming off of it. Okay, carbon won't have, by the way, carbon won't have 4 individual dashes. Okay, that's just won't have that. Okay, so who else can have this kind of situation? Silicon. All right, so silicon can have, and whoever else is under silicon and carbon. So silicon can have 4 bonds. It can be 4 single bonds, 2 single bonds, double bonds, and so forth. Okay, the elements in the 15th, which should be 15th column, they have 3 holes, so they have 3 bonds, and they have 1 lone pair. So that's nitrogen, and if you go back and look at the examples I gave you, at least 2 of them, ammonia, all right, had 3 bonds and 1 lone pair. Okay, cyanic acid had hydrogen with 3 bonds and 1 lone pair. And one we didn't show, but it's possible, is that you can have a nitrogen with 1 bond and 1 double bond and 1 lone pair. Again, this could be as a check. And phosphorus and other elements under nitrogen can have the same setup. Okay, oxygen is found in the 16th column. It has 2 holes, and it has, therefore, can have always 2 bonds, and it has 2 lone pairs. Okay, and we saw this arrangements for carbon. For instance, when you go back, when you look at formaldehyde or carbon dioxide, you saw oxygen with a double bond, 2 bonds, and 2 lone pairs. And then when you look at the case of water, the oxygen in water had 2 bonds, 2 single bonds, and 2 lone pairs. So again, anything under our oxygen can have the same thing. So if you see sulfur, it will have these 2 possible arrangements. Okay, and you can use this as a check to help you figure it out. And then fluorine has 1 hole. Okay, if you know, so again, this is, you have the Lewis dot structure for fluorine was this. Okay, and so it has 1 unpaired, and there's a hole there. Okay, so it has 1 hole, so it can have 1 bond. So right there. It has 3 lone pairs. It's in the 17th column. All right, so it'll only form a 1 bond. All right, okay, and everything underneath it, chlorine, bromine, and iodine, will have the same behavior. Have 3 bonds and, 3 lone pairs and 1 bond, 1 bonding arrangement. So if you look at this, carbon has 4 arrangements, 4 bonds. Nitrogen has 3 arrangements, 3 bonds. Oxygen has 2 arrangements, 2 bonds. Fluorine, 1 arrangement and 1 bond. And hydrogen also has 1 bond, 1 arrangement. Okay, so this is a good check. So when you come up with your bonding structures, use this as a check. There can't be you can't have, hydrogen with 2 bonds. You can't have fluorine with 2 bonds. You can't have oxygen with 3 bonds. So check your answer. Just, you should be able to answer your own questions when you get to this. All right. So that actually ends coming up doing bonding structures. There will be a worksheet, and I'll send out the answers and as a PowerPoint to you as well. There will be 2 more lectures. One will talk about the next one will talk about now that I have the bonding structure, the two-dimensional structure of these molecules. So the bonding structure is two-dimensional structure. Next thing to do is to relate that to its three-dimensional structure, and therefore its function. Okay, which will be and we'll come up with more structural information in the next, not just its three-dimensional structure, but more information. So this PowerPoint will be another PowerPoint about this, and finally, function of molecules, specifically interactions, how molecules interact. Okay, so that's it for this one.